2n factorial divided by law of indices here, 2 raised to power 2n, the law of indices n factorial squared, which is what the question asks us to establish. I want to believe you are following the pattern at which all these examples are being solved, and I'm sure that you are happy about this. So we move on to take some other questions. Question number 5. We have to show that summation n from 0 to infinity Pn cos theta is half cosec theta over 2. Cosec theta over 2. Hence, or otherwise, establish that A P2 of cos theta is 1 over 4, 1 plus 3 cos 2 theta, and B that P3 of cos theta is 1 against 8, 3 cos theta plus 5 cos 3 theta. So let us look at all this. If you look at the left hand side of the question A, we have it looks like our generating function. However, there is no t here. We can take t equals to 1 and our x equals to cos theta to generate this result. Let's see. I think that should work. Solution. Summation Pn of x t raised by n from 0 to infinity is the same thing as 1 divided by square root of 1 minus 2xt plus t squared. Now put t equals 1 and x equals cos theta. That gives summation Pn of cos theta from 0 to infinity equals 1 divided by square root of 1, that is 2, minus 2 cos theta. That's what we have. Now, looking at that, we observe that 1 divided by square root of 2 is common, and we have 1 divided by square root of 1 minus cos theta. From the knowledge of our half angle, we can write this as 1 divided by square root of 2 multiplied by 1 divided by square root of 2 sine square theta over 2. Yes. So root 2 multiplied by root 2 will give us half, and the square root of sine square is sine. 1 divided by sine will give us cosine. So that gives the result. Yes. That gives the first part of the result. Oh, that's good. Very interesting. Equals 1 over 2 cosec theta over 2, which is our desired result. Now the question says that hence we can use the established result. And what's the established result? That is summation Pn of cos theta n from 0 to infinity. Or otherwise, that is use another style or another established result elsewhere to show what we have here. The first example, one of our earlier examples, I have used ends. Let me use otherwise here at least to see what is going on. We know A now. Recall that P2 of x is 1/2 3x squared minus 1. Yes. If you put x equals to cos theta, P2 of cos theta becomes half 3 cos square theta minus 1. Now, if you look at the final answer, let me, my viewers should look at this. Please verify this. Let me just solve that first one in order to save our time. Where we are going to is 1/4, 1 plus 3 cos 2 theta. In terms of double angle, recall that in terms of double angle, cos square theta is cos 2 theta, or let me put it away, 1 plus cos 2 theta all divided by 2. Substitute that into the expression. P2 cos theta becomes 1/4 into 3 bracket 1 plus cos 2 theta minus 2, which will give us 1/4 into 3, that is 3 minus 2, 1 plus 3 cos 2 theta, which is what the question asks us to establish. And that is the solution of question number 5. Let's take more questions. Let's take more questions. Oh, this is an interesting question. Let me remove this. Question 6. Prove that summation Pn of x, n from 0 to infinity, equals square root of 2 divided by 2 f of lambda, comma, half semicolon lambda semicolon x, where lambda is arbitrary. First step. Solution. This is a typical of what I explained last time while we are solving a particular question. I think question number 4, if I'm not wrong. So let's look at this question. Of course, the question still suggests that we are going to make use of generating function because of the summation that we have. And how do we use the generating function from here? The left hand side, there is no t. That's what we need to observe. Meaning that our t has been taken as 1. Let's take t as 1 and let's see what is going to happen. If we take t as 1, recall that summation Pn of x t raised to power n from 0 to infinity equals equals 1 divided by square root of 1 minus 2xt plus t squared. Put t equals 1. It implies that we have summation Pn of minus Pn of x t raised 1 raised by n is 1, n from 0 to infinity equals 1 divided by square root of 1 plus, that is 2 minus 2x, which is 1 divided by square root of 2 into 1 minus x raised to power minus half. We've done a similar thing today, so I may not necessarily show the expansion here. The expansion gives, rationalize that one, it is root 2 divided by 2, and that gives summation half sub n divided by n factorial x raised to power n from 0 to infinity. Now, I can now create an arbitrary value, factorial functional value, by saying that I have this as lambda, that's what the question uses, divided by lambda sub n factorial n from 0 to infinity x to the power n. This is without loss of generality. We are not losing anything out. And that can be written out as root 2 divided by 2 f lambda, comma, half, semicolon, lambda, semicolon, x. And that's solved question number 6. That's solved question number 6. Let's take 4 more questions. Let me make it 10 questions today. Let's take 4 more questions. Question 7. Show that before question 7, suppose the question is summation minus 1 raised to power n Pn of x n from 0 to infinity. What will be our answer? What will be our answer? Please try this one out. Try this one out. What will be the results? Following the same pattern in terms of hypergeometric function. How would the result look like? That's going to be an interesting result. So try that out. Show that integral between minus 1 and 1 we will likely use orthogonality property here. 1 minus 2xt, let me conclude the question, t squared, the x gives 2 raised to power tn divided by 2n plus 1. We'll have to make use of that. How do I know? From here, number 1, the integral is only from minus 1 to 1. If you now look at the result, suppose I remove this. It is a well-known result that we are going to have square integral of minus 1 to 1 Pn of x squared dx will give us that result. So most likely during the course of our solution we are going to generate this. Let's see how it looks like. Yes, this is a very good question. Orthogonal property 3 raised to power n. Solution. Let me start from the left hand side. Integral of minus 1 to 1 Pn of x divided by square root of 1 minus 2xt plus t squared dx. Let's write it this way first. Let's separate integral minus 1 to 1 Pn of x multiplied by 1 divided by, oh, I see, 1 minus 2xt plus t squared dx. Yes. What I have here, let me put it in a box. Or let me write it this here. 1 divided by square root of 1 minus 2xt plus t squared defines something. And what does it define? It defines our generative function. So we are going to make use of that relation at that point. And what will that one give us? It gives minus 1 to 1 Pn of x. Let me enclose this one in a bigger bracket. Summation Pn of x t raised power n from 0 to infinity dx. Oh, the result is almost out. So from that point, what do we do from here? From this point, this is summation. We can substitute, yes. Let us substitute for each value of n into Pn and t. Into Pn and t raised power n. Bearing it in mind that what we are integrating is variable x, not variable t. Substitute. What we are going to have here, we have everything equals integral minus 1 to 1 Pn of x. The first one is P0 of x, P1 of xt, P2 of xt squared. It continues until I get to Pn of x plus Pn plus 1 of x, Pn of x t raised power n plus Pn plus 1 of x t raised power n plus 1 plus it continues. So let's close it that way. Dx. Now open the bracket and integrate simultaneously. If I open the bracket and integrate, this is what is going to happen. N and 0 are not the same. By orthogonality property, this gives 0. If I bring Pn and P1 together, the subscripts are not the same. The integral between minus 1 becomes 0. Similarly, same thing here. It will continue that way until we get to this point. N and N are the same. Let us leave that. Let's move on. Every radicand does not have the same subscript weight what we have outside the bracket. So their integral using orthogonality property becomes 0. So what we are left with is integral minus 1 to 1 Pn of x, everything squared. Let me take t raised power n outside, then the x is not an integral variable, so we can take it outside the integral sign. If we integrate this from orthogonality properties of the Legendre polynomial first kind, we will generate this one as 2 divided by 2n plus 1, multiplied by t raised power n, and that gives the final answer. That gives the final answer. Let's take another question. Let's take another question. Question 8. Question 8. 8. Suppose a polynomial f of x of degree n can be written as f of x equals summation Cn Pn of x n from 0 to infinity, where Pn of x is a Legendre polynomial of first kind. First kind. Full stop. Establish that Cn can be written as 2n plus 1 divided by 2 integral between minus 1 and 1 f of x Pn of x dx. Very nice question. So let's look at that. Let me see. Cn is what we have to get, and f of x Pn of x. Okay. We multiply this one by Pn. We multiply this one by Pn. Then okay. Solution. From the question, we are told that f of x is summation Cn Pn of x, n from 0 to infinity. Now, let us expand the right hand side. This is C0 P0 of x plus C1 P1 of x, similar to question 7, C2 P2 of x up to Cn Pn of x, plus it continues. Multiply both sides by Pn of x. F of x Pn of x is C0 P0 of x Pn of x, C1 P1 of x Pn of x, plus it continues until I get to Cn Pn of x all squared, then it continues. Now let us integrate between minus 1 and 1. Integrate between minus 1 and 1 of f of x Pn of x dx. By the principle of orthogonality property, this becomes 0, this becomes 0, every other term becomes 0 except this. And that is what we are going to integrate. Cn minus 1 to 1, Pn of x, everything squared dx. Which will give us 2Cn divided by 2n plus 1. Making Cn subject of formula, the result follows. Make Cn subject of formula, you have that result. So let's take question 9. Let's take question 9. Question 9. Show that integral, indefinite integral of Pn of x dx is the same thing as 1 divided by 2n plus 1 Pn plus 1 minus Pn plus 1 of x minus Pn minus 1 of x. Solution. This we need to use recurrence relation. Let me write this one very well, properly. 2n plus 1. If the result is this, that means that originally this should be a derivative. This also should be a derivative. Any relation Yeah, recall. Recurrence relation. That 2n plus 1 of Pn of x is the same thing as Pn plus 1 prime of x minus Pn plus minus 1 prime of x. Yes, that's the relation. Integrating both sides. This question is too simple. Integrating both sides. The result follows. It's a very simple question. That will give us Pn of x dx equals 1 divided by 2n plus 1. Integral of this one will give us Pn plus 1 of x, and integral of the second one will give us Pn minus 1 of x. That is the result. It is established. And lastly, under the example, number 10, evaluate the integral minus 1 to 1 x Pn of x and Pn plus 1 of x dx. Solution. We have to use orthogonality property here. How do we use that? There are three terms here. We have x, we have Pn of x, we have Pn plus 1 of x. We need to look for a recurrence relation that combines Pn and Pn plus 1, or probably xPn or xPn plus 1. So we have three options. The one that has xPn, x and Pn, the one that have x and Pn plus 1, and lastly the one that contains Pn and then Pn plus 1, or we can get the one that have the three of them. Let's start with the first recurrence relation we solved in the last class. That recurrence relation gives that Pn plus 1 of x is 2n plus 1 divided by n plus 1 x Pn of x minus, we have this, minus n divided by n plus 1 Pn minus 1 of x. Yeah, that's the recurrence relation. We can make use of this. If we make use of this, we are going to run into serious trouble, because we have to battle with x multiplied by x, which is x squared. That's going to be the major concern there. If we make xPn the subject of the formula at this spot, we don't have to battle with x again for the integration. So that is much easier. So let's make xPn of x the subject of the formula. If we make, let's be very sure. If I make this one subject of formula, for instance, I have this one multiplied by this, then I have to deal with x squared and Pn squared. Okay, let us make x Pn of x subject of the formula. And what will be the results? X Pn of x will give us m plus 1 Pn plus 1 of x plus n Pn minus 1 of x all divided by 2n plus 1. So this now implies that integral minus 1 to 1 of xp n of x Pn plus 1 of x dx becomes 1 divided by 2n plus 1 outside of the integral minus 1 to 1. I have Pn plus 1 of x into n plus 1 Pn plus 1 of x plus n Pn minus 1 of x everything dx. What does that one translate to? We have the same substitute here. That cannot be 0. By orthogonality principle or property, this becomes 0 under the integration. They have different subscripts. So that means that I have this one to be n plus 1 divided by 2n plus 1 integral minus 1 to 1 Pn plus 1 of x everything squared dx, which gives n plus 1 divided by 2n plus 1 multiplied by 2 divided by 2 into n plus 1 plus 1. And the final result for that integral is the final result for the integral is 2 into n plus 1 all divided by 2n plus 1 into 2n plus 3. And that is the final answer to that question. That's the final answer to the question. So far today, we have been looking at Legendre polynomial. Throughout today, our focus has been giving examples, different examples, to illustrate what we have explained in our previous classes as far as Legendre equations and one of its solutions, which is Legendre polynomial and its property, is concerned. 10 questions of different difficult level of different variety of questions of different level have been solved in today's class. It is my hope that if we take textbooks, we will be able to solve as many problems as possible. Against our next class, I want us to read ahead of that class and look at the next tool as far as Legendre polynomial first kind is concerned, and that is Rodrich's formula. Till that time that we are going to be meeting, I wish you all best of luck. Thank you for listening and thank you for your time.